Hey there. Hello there. Once again, I welcome you. This is Sudhanshu Tripathi. Those who are new to my channel, I am a retired teacher in chemistry, teaching in college level, and I have been busy preparing video lectures for the YouTube. And those who are already subscribers, they have been watching to me, and many have given constructive ideas how to improve my video, and also have found out some errors at the point I commit, because to err is human. So I might have committed a few mistakes while I deliver, or even there can be a slip of my pen. So I request those viewers who watch with all sincerity to point me out where I have committed any error. Now, if you have not yet subscribed to my channel and you are a regular viewer, I definitely will request you to subscribe. Not only like, but also subscribe. Just click on the subscribe button. That's it. Today's topic is very fascinating, because all my video lectures are particularly meant for the last level schoolgoers, class 11 and 12, a transition from school to the university. I prepare video lectures for them. So today's topic is very fascinating. Particularly, it is a subject matter of interest for higher level and graduate level, but I would try to restrict my discussion in a very rudimentary extent. Now, what the topic of my lecture is something like this: selectivity versus specificity in organic reactions. This is the part 1 where we talk about regioselectivity and stereoselectivity. Often there is a confusion by many, and many have asked me particularly what is the difference between stereoselectivity and stereospecificity. Can they be interchangeably used, or you are restricted to use one for one case and the other for the other case? Let's start. Now, regioselectivity is to do something with the product's structure. If a reaction is regioselective, it gives more than one structural isomers, or constitutional isomers, or also called regioisomers, in unequal amounts. You have two isomers, structural isomers, but in unequal amounts, then we call it a regioselective reaction. For example, the dehydrohalogenation of 2-chlorobutane, applying the Sadzev rule, you get but2-ene and but1-ene. These are the two products, but the major product is but2-ene. More substituted alkene is the major product. So when you have two structural isomers, but2-ene and but1-ene, and but2-ene is in larger quantities, then we brand this as a regioselective reaction. If only one isomer is formed out of the two possibilities, in addition of a polar addendum to an unsymmetrical alkene, you have two possibilities. The negative part goes here or there. The positive part goes here or there. So there are two possibilities. If one of the products is produced in almost exclusive abundance, nearly 100%, then we can use the term regiospecific. So regiospecific is the extreme limit of regioselective. Otherwise, there is no point in misusing the term regiospecific if you are not sure that the percentage of one is nearly 100% and the other is almost extinct. Now, let me remind you what is the difference between and what is stereoselectivity. Before I remind you about the difference between structural isomers and stereoisomers, I would like to define what is stereoselectivity. A reaction is stereoselective if it gives more than one stereoisomeric products. It may be enantiomers or S. It gives both, but one of them in larger quantities. Or the two diastereoisomers, one of them being a larger quantities in unequal amounts. So there, regioselectivity is to do with structural isomers, but but stereoselectivity is something to do with stereoisomers, like L-lactic acid, D-lactic acid, plus lactic acid, minus lactic acid, or say R-lactic acid, S-lactic acid. Lactic acid is one, structure is same, but its stereo designation is different. Or the two are diastereoisomers, cis-butene or trans-butene. You get mixture of cis and trans, but trans is at a higher percentage. So that is called a stereoselective reaction, where you get two stereoisomeric products but in unequal amounts. And when we call a particular reaction as stereospecific, it is something to do with both reactant and product. In stereoselective, we are nothing to do with the reactant. The reactant may be a stereoisomer or may not have any feature of stereoisomerism, and there might be no chiral center or no double bond which will show cis and trans. So still the products can be stereoisomers. So stereoselectivity is nothing to do with the identity of the stereo identity of the reactant. But in stereospecific reaction, not only one of the stereoisomers is formed exclusively, but also the reactant should be also is to be unique. A unique stereoisomeric reactant will produce a unique stereoisomeric product. That means the reactant has to be a stereoisomer, and if one stereoisomer gives this product, then the other stereoisomer gives that product. So both the reactants are stereoisomers, mostly they are diastereoisomers, and the products are also diastereoisomers. But reactant and product, they are different. So if a fixed stereoisomeric reactant gives a fixed stereoisomeric product, not a mixture of two, fixed, then we can call it a stereospecific reaction. We should call it as a stereospecific reaction. But stereospecific term is often loosely used. When stereoselectivity is 100%, then we often use the term stereospecific, but it's not according to the accepted definition of stereospecific reaction. And some authors, some instructors, they use the term stereoselective reaction or stereoselective process even if it is a stereospecific reaction. There is a lot of confusion, therefore, in the young minds, in the minds of the beginners, where to use the term stereoselective and where to use the term stereospecific. While they study in different literature, different sources, listen to different instructors, they are confused. Some people use stereoselective for stereospecific and stereospecific for stereoselective. So don't be critical about it. You understand the concept perfectly, then you figure out what term suits you the most. Let us start. Now, what is the difference between structural isomers and stereoisomers? If you have not studied much about isomerism, you can view my videos on stereoisomerism, particularly stereoisomerism. Otherwise, there is no point in wasting time here. And supposing I take, say, but 1-in and this is but 2-in. Tell me, these are structural isomers. Their names are different. This is 1-in, this is 2-in, this is 2-in. So they are structural isomers. So if these two are formed in a reaction with varying with unequal amounts, then that is regioselective. If only one product is formed, but there was a possibility of the other product, but somehow the reaction passes through such a crucial, such a unique pathway that only one structural isomer was formed and the other was completely eliminated. In that case, you can use regiospecific, otherwise regioselective if both are formed. But what about stereoisomers? Supposing but 2-in, you have two but 2-in. You cannot say but 2-in, everybody will laugh at you. But 2-in exists in two geometrical forms, two diastereoisomeric forms. One is the cis but 2-in and the other one is the trans. And this is close to each other, cis, we call it Z, and this is trans, or E. I'm not going to talk more about cis and trans, Z and E, but these are stereoisomers, and that too diastereoisomers, and you can call it geometrical isomers. And what about the optical isomers? Supposing you have a chiral center like this. This carbon is bonded to 4 different groups, an asymmetric center, a chiral center. Say this is CH3, this is COH, this is OH. You know, this has a particular configuration, say R or S. And we can use the CIP rule to find out its absolute configuration. This is priority number 1, this is 2, this is 3, this is 4. So the rotation, the I rotation is anticlockwise, and this is S. The configuration here is S. And if you make a switch of any two groups, you get its mirror image, non-superimposable mirror image. And the configuration of this will be the opposite. If this is S, this is R. So these are stereoisomers, and these are called enantiomers. These are mirror images of each other, and they are not superimposable. And what are diastereoisomers in optical activity? Supposing there are 2 chiral centers. Supposing this is COH, this is COH, this is H, this is H, this is OH, this is OH. And here there is a plane of symmetry. This is a mesoform. This has got some configuration R or S. This is another configuration R or S. It has to be, if this is R, this is S, because they have to be opposite, because there is a plane of symmetry. So due to internal compensation, there is no optical rotation, although there are two chiral centers, right? Now, if I make one switch at any one chiral center, supposing I bring OH here, H here, I made one switch, then I got another diastereoisomer. This is an active form. There is no plane of symmetry, and this is an active form, either RR or SS. So these two are diastereoisomers. And this has got another mirror image form. You make one switch at each chiral center, you get its mirror image. They are enantiomers. I am not drawing its enantiomer. I am showing that this is one mesoform, this is inactive and this is active, either RR or SS. Let us not waste our time in finding the configuration whether it is RR or SS. If this is RR, then the mirror image will be SS. But these two, which have at least one chiral center identical and other different, at least one chiral center is common, is identical, then they are diastereoisomers. Their properties, physical properties are all different, as you know. So, in stereospecific reaction or stereoselective reaction, you have to deal with this. If it is stereoselective, it can be enantioselective. Two enantiomers are formed, one of them in larger excess. Two enantiomers are formed. I have not drawn the enantiomer of this compound. Two enantiomers are formed, and one of them in larger excess. That is enantioselective. So, stereoselectivity has two aspects, enantioselective and diastereoselective. If these two are formed in a reaction and one of them is in larger excess, then that is called diastereoselective. Now, as you know, if there is no plane of symmetry, supposing there is a group different from carboxyl group, supposing this is say methyl. So then this is not a mesoform, and this is also an active form, and it has its mirror image. Supposing this is RS, this will be SR, and this has also its mirror image. If it is RR, the mirror image is SS. And as you know, one of these and one of these, they are related as diastereoisomers. You know. So, if the reaction is diastereoselective, then you will find two diastereoisomers in the product, and one of them is in larger quantities. Let us start. I have already told you, many authors do not use the term regiospecific because the data are not available in many reactions, and hence they do not like to run a risk of misusing the term, because if one of them is not 100%, then how can they with all conviction say it is regiospecific? To me, if one isomer is formed almost exclusively, more than 99% for example, then it should be called regiospecific. This makes a good distinction between those in which both the products are formed in appreciable quantities. They should be called regioselective, but if almost exclusively one of the products is formed almost exclusively, nearly 100%, then we can dare use the term regiospecific. For example, reaction of propene with HCl gives isopropyl chloride almost exclusively as 2 degree carbocation is far more stable than 1 degree carbocation, as the reaction is electrophilic addition mechanism. Let's proceed further to see what is happening here. And similarly, elimination by E2 mechanism is regioselective. For that we use the Sajef rule. So whenever you have a 2-chlorobutane is treated with a strong base like alcoholic KOH, there is elimination. Say there are two possibilities. Here is one possibility, of elimination. This is called beta elimination, and the mechanism is E2. Forget the mechanism, whether it is E2 or something else. So if you have not studied the detailed mechanism of elimination, you forget. So the double bond can be put here to form butene, and there is another possibility where in other molecules where this hydrogen will go and the double bond can be formed here. So this is but2ene and but1ene. These are structural isomers, and it is 80% but2ene and 20% but1ene. So therefore this is a regioselective reaction. Later on we will see that out of the two cis and trans of the measured product, cis will be lower, trans will be in higher percentage. So again it will be stereoselective for the measured product. So the reaction is not only regioselective but also stereoselective for the measured product, right? Some other cases where you find the anti-Surjev product is measured. You will know about all this in your subsequent courses. That in some other cases, for example, here this is a quaternary ammonium salt hydroxide. When heated, then you get the less substituted alkene, the anti-Surjev product being the major one. Here but2ene was major, here but1ene is major, and but2ene is the minor product. So whatever may be the case, the mechanism is E2 and it is a regioselective reaction. Both the products are present. Not one is completely eliminated or extinct. Now let's proceed. Addition of a polar addendum like HX, HCl, HBr, HI, or water in presence of acid to simple, I emphasize simple unsymmetrical alkenes is regiospecific. I dare use the term here because although the authors they do not find data supporting their conviction whether there should be regioselective or that should be regiospecific, I will support with a strong logic that whenever there is a chance of forming 2-degree carbocation in the face of 1 degree, it is 2-degree carbocation which is formed. Similarly, I am just showing you here these reactions. When this alkene is simple, no substitution, nothing, is simple. This is propene. Then you add HCl. So in the electrophilic addition mechanism, as I have already made a video on that. So first part is the formation of the carbocation. So either carbocation will be formed here, that is 2-degree carbocation, or it will be CH2 here and this is CH2 plus here. In that case, it would be primary or 1-degree carbocation. So as you know, there is no chance of 1-degree carbocation formation when there is a chance of 2-degree. So therefore, the nucleophile will later join here, and the only product we expect for this simple alkene is isopropyl chloride or 2-chloropropane. Similarly, this is isobutene. When you add HCl or HBr, the only product is 3-degree tertiary butyl chloride, not isobutyl chloride. Because when hydrogen is bonded here, then plus charge will be created here. That is a 3-degree carbocation. Mind you, 3-degree carbocation is extremely stable compared to other degrees carbocations. Therefore, there is no chance of forming a 1-degree carbocation, and this will be 100%. This will be 100%. Therefore, I can dare say it is regiospecific. But in many other cases, when the alkene is symmetrical, carrying same number of hydrogen atoms on both the sides of the double bond, in that case you get appreciable quantities of both the products, both the structural isomers, both the regioisomers. In that case, you have to use the term regioselective. For example, you see, this is the case of hex 2-ene, 1, 2, 3, 4, 5, 6. So, and the number of hydrogen atom is same. You cannot apply the Markovnikov's rule here. You have to go via the mechanism. So if I comes here, H joins here, I comes here. This is 2 iodohexane. And if H joins here, I comes here. This is 3 iodohexane. But since both are secondary carbocations, they are almost equally stable. And therefore, the percentage is nearly 50%. I do not have the data with me for this. From my experience, I can tell you that the percentage will be nearly 50%. Although, if you can argue the relative stability of this carbocation and this carbocation, taking hyperconjugation effect into our discussion, there are 3 plus 2 alpha hydrogen atoms, 5 alpha hydrogen atoms. And if plus would have been here, then the number of alpha hydrogen atoms is 4. So therefore, there is a slight greater chance of I minus the nucleophile joining here, as the carbocation stability is slightly, relatively more stable. But we cannot say, we do not know actual percentage. So we will say it is a non-regioselective process, because 50-50. Let us presume that it is 50-50. If it is 50-50, then it is not selective. It is a non-regioselective reaction, although the products are stereoisomers. Or you can say it is poorly regioselective. But look to this. And you will be knowing, if you do not know, forget about it. If you will be knowing in your future organic programs that an addition, elimination, substitution, when there is a formation of carbocation, there is always an ample room for its rearrangement. From a less stable carbocation, it will be promoted to a more stable carbocation by either a hydride shift or by a alkyl shift. So this happens here. This is a symmetrical 2 degree, 2 degree. So there are 3 products. The Cl can join here, Cl can join here. A lay student will do that. Double bond is here, so the 2 possibilities, because it is a symmetrical alkene with respect, as regards to the number of hydrogen atoms. So no Markovnikov's rule. So both the products will be formed. But interestingly, both the products that we talked about now are the minor products. The major product is due to the hydride shift. These hydrogen shifts here, and ultimately carbocation, 3 degree carbocation is formed here, and ultimately chloride ion joins here, so chloro group joins here. So the 3 degree, so the 3 degree product will be the major product. So in this case, we get 3 regioisomers or structural isomers, unequal quantities, then we can call it is regioselective process. But here it is either poorly regioselective or it is non-regioselective, right? But when alkene is a very simple alkene, like propene, like but1ene, so there is no possibility of formation of a 1 degree carbocation. So you can say it is regiospecific. Still, I tell you, if you are not very confident, then you can use regioselective, but I will not. Now let me rub it off, because I have already explained. So this is 100%. So let me clean it for future use. Let me also clean this. So we are going fast in our discussion. Now, what I had written, regioselectivity or regiospecificity is something to do with the formation of different. It's nothing to do with. Is something to do with the formation of structural the regio term, whether it is regioselective or regiospecific, something to do with structural isomeric products, or the constitutional isomeric products, the regioisomeric products. It speaks nothing about the stereo identity of the reactant or product. You can call highly regioselective. If you are a little scared of using the term regiospecific, you can call it highly regioselective. Even, I tell you, even for the case of formation of this third butyl chloride or isopropyl chloride, many authors call it regioselective reaction, highly regioselective, because they do not have the data, so they cannot have the confidence to say that it is 100% and regiospecific. So you can use highly regioselective if you are not confident, not sure about it. So selectivity, regioselective term is a safer term. You can call it highly regioselective as a regioselective. That will mean regiospecific, but don't use the term regiospecific if you do not have the supporting data, right? Then let us proceed discussion more on stereoselectivity. Stereo. When the products are stereoisomers and one of them is formed in larger quantities than the other, it is called stereoselective reaction. Addition of water to butene in presence of acid is a non-stereoselective, because you get a 50-50 mixture of D and L. You get the two enantiomers, no doubt, but no preference, no predominance of one over the other. Therefore, if it is 50-50, even if they are stereoisomers, that reaction is not stereoselective. It is non-stereoselective. Stereoselectivity is something to do with the stereo identity of two different stereoisomeric products. It also doesn't speak about the stereo identity of the reactant. The reactant may not be a stereoisomer. It may be a simple reactant. But if the products are stereoisomers, either enantiomers or diastereoisomers, and they are formed in unequal quantities, then it is very, very safe to use the term stereoselective. And if it is really highly stereoselective, if one of the stereoisomers is present in very large quantities, nearly 100%, say 99%, it is safer to use the term highly stereoselective rather than using the term stereospecific, because stereospecific has a very, very special definition. We will be talking about that in our subsequent video. Next video, I will be talking only about stereospecific reaction. But now I want you to familiarize with the term stereoselective. Whenever you get two stereoisomeric products in unequal amounts, always use the term stereoselective. For example, this is but1 and this is water in presence of acid. Addition will be definitely giving you a 2-degree carbocation. So almost 100% you get butan-2-ol. But butan-2-ol is a chiral molecule. There is a chiral center. So the reaction is regiospecific. So far as this structural isomer is concerned, I have not written butan-1-ol. It is totally extinct. It is regiospecific because, yes, I dare say that, because when there is a chance of forming 2-degree carbocation by the addition of H plus here, there is no chance of 1-degree carbocation, and there is no room for any rearrangement here. If there will be rearrangement, the product will be again same. So butan-2-ol, but looking to the two different butan-2-ols, that is R-butan-2-ol, S-butan-2-ol, D-butan-2-ol, L-butan-2-ol, you find it is a 50-50 mixture. So it is non-stereoselective. Had it been 70-30, 60-40, 80-20, then it would have been a stereoselective reaction. But the reaction is regiospecific because the other structural isomer, butan-1-ol, doesn't form. Similarly, a ketone like a pentan-2-on, 1, 2, 3, 4, 5, 1, 2, 3, 4, butan-2-on, I'm sorry, when it is reduced by any reducing agent like lithium aluminum hydride, followed by acid workup, you will find this is a planar site, And similarly, carbocation is also planar. Whenever there is a planar site, either the intermediate species or the molecule itself, then the attack by the reagent can happen from both the sides, from above or from below, with respect to that plane. Therefore, if one attack will be giving you R, the other attack will give you its mirror image, enantiomer S. So therefore, this is also 50-50. So it is non-stereoselective. So whenever the reaction passes through a planar state, maybe a carbocation, or the molecule itself has a planar site, like the ketone or aldehyde I have shown, then it results in perfect racemization or a DL mixture, as there is a 50% probability of attack from either side of the plane. Right? So let us proceed. Let us see some reactions which are highly stereoselective. I can tell you it is 100% almost one of the products. The other product may be less than 1%, but still we cannot use the term stereospecific. We can call it highly stereoselective reaction, but some people interchangeably, and I can say loosely, use the term stereoselective for stereospecific, stereospecific for stereoselective. That's the reason why I'm just making the concepts clear to you, so that you maintain caution while you yourself will use the term. Addition of hydrogen to alkyne triple bond, for example but2-wine, in presence of a poisoned Lindlet's catalyst or a P2 catalyst. I am not going to discuss about these catalysts now. Give exclusively the Z alkene, that is the cis alkene, due to the cis addition mechanism or the syn addition mechanism. Both the groups added with respect to the double bond, they are added from the same side, either both from the top or both from the bottom. So that gives you the Z alkene. On the other hand, if we use another reducing agent, sodium liquid ammonia, the mechanism will be anti. If one hydrogen will come from the top in this carbon, then the other hydrogen will approach from the bottom in the other carbon. So it will be giving trans alkene. So liquid ammonia, sodium liquid ammonia is treated with but2-wine, will give you trans but2ene, that is E-but2ene, but the P2 catalyst or Lindlet's catalyst will give you Z or cis but2ene. Some instructors and authors use the term stereospecific for these cases, but which is incorrect, since the alkyne has no stereo identity. So strictly the term stereospecific cannot be used according to the accepted definition of stereospecific reactions. We will discuss in the next video. We can call it highly stereoselective. Because the percentage of the other one might be less than 1%. We do not count that, but we cannot say that it is 0. It is there, and it doesn't satisfy the definition of the stereospecific reaction. Done it? Now the same thing I was saying, this is the Lindlet's catalyst, palladized barium sulfate or calcium carbonate, poisoned by quinoline, lead acetate or sulfur, then you get cis Z, and if you take sodium liquid ammonia, it will give the trans. The product, the reactant is the same one. There is no stereoisomeric reactant. Had it been a truly stereospecific reaction, then these two would have been stereoisomers, which is not possible in case of alkynes. Therefore, strictly you cannot use the term stereospecific. I have already told you in the beginning, during my introductory discussion, that stereoselectivity is of two types. If the products are the mirror images or the enantiomers, then that stereoselectivity is called enantioselectivity. And if the two products are diastereoisomers, then the stereoselectivity is called the diastereoselectivity. And now research is being extensively done in this area, chiral synthesis or asymmetric synthesis, where you get a mixture of enantiomers, but one having a preponderance over the other by using chiral catalysts. If the catalyst is itself chiral, then it influences the formation of one of the product enantiomer or diastereoisomer in favor, in a greater percentage than the other. There can be other reactions without involving chiral catalyst that can also be stereoselective, either enantioselective or diastereoselective. Let's see. In one of my earlier videos, I have discussed about homotopic, enantiotopic and diastereotopic hydrogen atoms. Now see, this is an achiral molecule. It's not a chiral one. But if you are substituting, I'm not giving you the reagent used for substituting. Supposing S will come, H will go, S is a substituent, will come, and H will go, and we have a catalyst that is chiral, that itself is chiral, or an enzyme, a biocatalyst. Then it can influence the formation of one enantiomer over the other. Supposing this is R, this is S, then R is favored in this reaction, maybe 80-20 or 70-30. In that case, it is enantioselective. That stereoselectivity can be branded as enantioselectivity. So the reactant may not be chiral or may not have any stereo identity, but the products are stereoisomers. They are enantiomers, therefore enantioselective. Now, see, this, you forget about this by NAP. This is a chiral reagent, a chiral catalyst. So when you are using a chiral and this is R, the chiral catalyst is R. You forget about this. This is a ligand which is chiral, which is bonded to ruthenium, a ruthenium ion, and that itself is the catalyst. This is R. So the product, this reactant was a chiral, this is a carbonyl group, and this is an ester function, and ester function is not reduced. So this reduction in presence of hydrogen occurs here. So there is a mixture of both R and S, but R is more than 99%. S is almost negligible. Still then you cannot call it stereospecific. It is highly stereoselective. The presence of this chiral catalyst favors the formation of one of the enantiomers, R, S product, where OH will remain below the plane and H will remain above the plane. H is not shown here. That is formed to a very, very negligible extent. Similarly, and I have just shown for the sake of fun, I've shown you this binap. This is a binaptyl compound. This is a chiral compound. This R is taken there, not S. This chirality is not due to any chiral center. This is due to chiral axis. Forget about the chiral and chirality. Now, this binap is this compound. This R is taken, the ruthenium complex, and when this is used, we get the R product predominating more, nearly 100%. Similarly, I give you another example. This is called the Sharpless Dihydroxylation. Sharpless, from the very name, the term Sharpless talks something different in a literary sense. But do you know Sharpless is the name of a scientist who got Nobel Prize in this, I think, 21st century. In this 21st century, I don't exactly remember, 2000 some odd, he got the Nobel Prize for this asymmetric synthesis. So many reactions he has done, he has introduced, he has discovered. One of them is using osmium tetroxide, alkene. You already know, if you have studied alkene, you know the reaction of Bayer's reagent cold dilute alkaline KMnO4, or osmium tetroxide gives the diol, bisphenol diol, the dihydroxy compound, and due to cis addition. That's already known. But what Sharpless did, Sharpless is the name of a scientist who got the Nobel Prize. What he found using a chiral catalyst, this is called admix alpha. It's a mixture of several things, like the osmium tetroxide in the salt form, potassium carbonate, potassium ferricyanide, and this alpha means this one. This is a chiral ligand, all mixture, admix alpha. That gives you this particular enantiomer RS. This is R, this is S. I am not spending time to find out the configuration because the groups are not known. This is large. Of course, we can find out. This is large size, this is small size, this is medium size. So we can apply the CIP rule and find out. I have done that before, but I am not spending time now. If you have got interest, you can definitely watch my videos on stereoisomerism. Now, this is SR. If you are using another chiral catalyst, that is called admix beta, you are using its enantiomer 100%, nearly 100%, say 99.5, this is 0.5, this one. And admix alpha will produce 99.5% this and 0.5 this one. So I have not written the 0.5% of the other. It looks as if it is stereospecific, but you are refrained because there is some. You could have written the term stereospecific because the reactant has a stereo identity, but since the other isomer is formed, enantiomer is formed to a very small extent, so let us better use the term highly stereoselective, enantioselective. Don't think that they are diastereoisomers. This is SR, this is RS. At each individual chiral centers, the configuration is opposite. So therefore, they are not diastereoisomers, they are enantiomers. So Sharpless did an amazing preparation of one particular enantiomer to the extent of nearly 100%. Can you believe it? Earlier it was 60-40, 70-30 is like that. There is a tilting of the formation on one side of the isomer, enantiomer or diastereoisomer. We have not yet talked about diastereoselective. Now let us proceed. Just another Sharpless dihydroxylation. This is an alkene. This is aromatic. So addition will not occur here. This is alkene where the addition will take place. So both are lying above. This is the configuration is RR and it is 98% RR. This is EE means enantiomeric excess is 98%. So only 2% is its enantiomer SS. So since this can also this doesn't have any stereo identity, so let us not use, and there is 2% of the formation of the other enantiomer, so let us call it highly stereoselective. And just for fun, I have shown you this DHQ whole 2 PAL, that is thalazine. This thalazine with dihydroquinine, and this is thalazine with dihydroquinidine. So this is a constituent of admix beta, and this is a constituent of admix alpha, and admix beta goes in one direction, favors almost exclusively one enantiomer. This favors the formation of the other enantiomer. These are chiral reagents. In fact, they are chiral ligands which are bonded to some metal ions, some transition metal ions like osmium, like that osmium, right? So I have already told you, say if you know about SN mechanism, SN1, SN2, if you have not studied the nucleophilic substitution, this is unimolecular or first order, that is non-stereoselective and also non-stereospecific. Although 2 enantiomers are formed, but to the extent of 50-50. It's a racemic mixture. It goes via carbocation. I told you, any reaction goes via carbocation. There is a 50% chance that the nucleophile will attack on this side, and another 50% chance the nucleophile will attack on this side. So both R and S is formed to the extent of 50%. So if the mechanism is pure SN1, which goes via carbocation, this is a substitution reaction. L is the leaving group, it goes away, and the new nucleophile will come. This should be minus. I'm so sorry, because Nu minus will come and L minus will go. This is nucleophile, this is leaving group, and it goes via carbocation. Then it is 50-50. So it is non-stereoselective. You cannot also call it a stereospecific, because if this, supposing this is R, it will produce 50-50, and S will also produce 50-50. But in stereospecific, the product should be different and unique. The products are stereoisomers, and the reactants are also stereoisomers. Yes, the reactants are stereoisomers in this case, but the product will be same, 50-50. Therefore, this is neither stereoselective nor stereospecific. Now, we are almost at the close of this lecture. I think we will not proceed more than let me see, it's 51 minutes, nothing to worry. Now, let us, the second part of stereoselectivity is diastereoselectivity, which has two facets, two aspects. One coming under geometrical isomerism, the other coming under optical isomerism. So, we already know 2-chlorobutane or any haloalkane or alkyl halide, particularly 2 degree and 3 degree, when treated with a strong base like potassium tertiary butoxide or alcoholic KOH, this is a solvent DMS. So you get but-2-ene as the major product. And but-1-ene, I have not written but-1-ene because about regioselectivity we have already discussed. It is a regioselective reaction. But looking to the major product, which is but-2-ene, you find the trans is in more quantity, 60%, 20%, 80%. What about the remaining 20? Remaining 20 is but-1-ene, which I have not written. So this but-2-ene, cis-but-2-ene and trans-but-2-ene, they are stereoisomers, they are diastereoisomers, and one of them is in larger quantity, so it is stereoselective. And what category of stereoselectivity is diastereoselectivity? So the reaction I told you is regioselective, but-1-ene I have not shown. Now, if there is already a chiral center, A, B, C, 3 different groups, this supposing it is R, it is fixed. And these 2 hydrogen atoms, as we know, they are called diastereotopic hydrogen atoms. And if some substitution occurs, say R comes here, by some way H goes and R comes, then another chiral center is created. So, if there is a chiral catalyst, or in some cases there is no chiral catalyst, simply the presence of one chiral center will influence the formation of one of the diastereoisomers in larger quantities. So, this particular chiral center can have 2 possibilities. It can be R, it can be S. Supposing this is existing R, fixed. This R, supposing this is R, this is S. So, if this RR is formed with 70% and RS is formed 30%, they are diastereoisomers, then this is also a stereoselective reaction, and that too it is diastereoselective reaction. But there are some cases where you need not have to use chiral catalysts. Chiral catalyst influences the reagent. I have not shown how R came. There must be some reagent having R, but you have to have a chiral catalyst to influence the formation of R for this chiral center over the S of the same chiral center. And supposing we take this example where there is an already existing chiral center, S, supposing this configuration is S, and a new chiral center will be created by the addition of ethyl magnesium bromide, a Grignard reagent, followed by acid workup. If you do not know about this, you forget, you will be knowing in your subsequent organic program. So there is no chiral catalyst, but the presence of an existing chiral center favors the formation of one diastereoisomer to a greater extent. So this is S, so the new one is S, so this is major, and this is S, the new one is R, is minor. So here there is no need to use a chiral catalyst. Similarly, here this curly sign indicates it can be both R or S. So if you take R and if you bring about hydrogenation, there will be two products. Either it will be, there will be hydrogenation happening here. This is fixed. This means either you can take R or S, whatever. So, supposing I have taken this above the plane, it remains as such, it will not change. So, it is there intact. But this can be above the plane, this can be below the plane. So, if they are on the same side, this is cis, this is opposite side, this is trans. So, trans has been found to be formed with a larger percentage. So, it is stereoselective, and that too diastereoselective. If this is RR, this is RS. If this is cis, this is trans. Got it? Now, the same example. If you reduce this carbonyl compound, this is another compound, this stereochemistry, this is a fixed S, this one, S is fixed. And if a new chiral center is created without the aid of any chiral reagent, chiral catalyst, simply this is the reagent which will bring about reduction here, the carbonyl group, you have an alcohol, secondary alcohol here, so this has been found to be major, SS, RS. This S is fixed. This S or R, this is found to be major. These are two diastereoisomers. Similarly, if another reagent is taken, the same compound, SS, another dimethyl magnesium is taken, it is found that SS is now 1% and RS is 99%. So it all happens due to the nature of the reagent and the influence of the existing chiral center on the formation of the new chiral center, tilting in favor of one configuration over the other. Similarly, you can have geometrical isomers. In cyclic compounds, we prefer to use the term geometrical isomers rather than optical isomers, although they have their absolute configuration RS. So when this configuration is fixed, supposing this is R, and you reduce this double bond, there are two possibilities. 68% is coming cis, and 68% is 32% is coming trans. So these two are diastereoisomers, cis and trans. Similarly, when you are making epoxidation, this oxide bridge, epoxidation using metachloroperoxy benzoic acid, MCPBA peroxy acid, then it is found that 3:1 ratio is the ratio of the two diastereoisomers. This is the trans product, the methyl and the epoxy bridge remaining on the opposite side. This is the same side. This is cis product, trans product. So this is also stereoselective, diastereoselective. But in this case, it is forming 1:1. So depending on the actual percentage formed, you have to brand whether it is stereoselective or it is non-stereoselective. Similarly, in bicyclic compound, it has been found that whenever you make a peroxy compound by using, this is MCPBA, metachloroperoxy benzoic acid. It is simply used to produce epoxy compound or alkene oxides. So the alkene oxide is formed when this is located to the side of the less hindered bridge, that is bridge having only one carbon atom rather than, this is called the exo product. If this is called the endo product, when any substituent or any thing is close to the longest bridge, then that is called the endo. and if it is on the opposite side of the longest bridge, that means it is on the side of the shortest bridge, then that is called the exoproduct. So in this case, always the exoproduct has been found to be major, this is minor. This is also a stereoselective reaction, diastereoselective, because these are diastereoisomers. One is cis and trans. Now we close, because I will be dedicating another maybe 30 minutes at the most for you discussing some important stereo specific reactions starting from its definition. Bye bye.